Have you ever stopped to think about what's really going on inside your computer? I mean, deep down. In this explainer, we're going to peel back the layers and follow the incredible, super fast journey of just one single instruction. We'll go from your click all the way to the final result on your screen and really uncover the hidden world that powers literally everything you do.
You click an icon, and it just works. It feels instant, almost like magic, right? But in those few milliseconds, a complete whirlwind of perfectly choreographed events kicks off inside your machine. So let's trace that single click and see how it all actually comes together. Okay, so before we can follow that instruction on its journey, we need to get one thing straight. We've got to understand the difference between a computer's blueprint and the actual building itself. It's this core distinction between the plan and the physical stuff that brings that plan to life.
This really all comes down to what versus how. The architecture is the blueprint. It's what the programmer sees. It answers the question, is there a multiply instruction? The organization, on the other hand, is the physical building. It's about how that multiplication actually gets done. Is there a special piece of hardware just for that? This is why a program from decades ago can still run on a modern processor. The architecture, the blueprint, is the same, even if the organization, the physical hardware, is completely different, way more advanced.
So every instruction's journey involves 4 key players, kind of like the main characters in our story. First, you've got the CPU, the brain of the whole operation. Then there's main memory, or RAM, which is like its short-term workspace. Input/output, or I/O, is how the computer talks to us in the real world. And finally, you have the system interconnections. Think of these as the superhighways connecting everything together.
All right, let's zoom in on the heart of it all, the CPU. This is where the magic really happens, through this relentless, looping cycle that is the true engine of all computation.
Inside that CPU brain, there's a whole team of specialists. The control unit is like the project manager. It goes out, fetches instructions from memory, and then figures out what on earth they're supposed to do. The arithmetic logic unit, or ALU, is the mathematician of the group. It does all the heavy lifting, all the calculations and logical comparisons, and then you have the registers. Think of these as a tiny, ridiculously fast workbench right next to the ALU, holding the exact bits of data it needs for whatever task it's working on right now.
So, at the very core of what the CPU does is probably the most fundamental process in all of computing, the fetch, decode, execute cycle. It is a simple 3-step dance that never, ever stops. Step 1, fetch an instruction. Step 2, decode it. Step 3, execute it. This loop repeats itself billions of times every single second, and it's what runs every program on your computer.
So how does the CPU know which instruction to grab next? Well, that's the job of the program counter. It's a special little register that does one thing. It holds the memory address of the very next instruction. As soon as one instruction is fetched, the program counter automatically ticks up, pointing to the next one in line. It's basically the conductor of the whole symphony, making sure everything happens in the right order.
Now, the CPU is the one doing all the processing, but it has to get those instructions from memory first. And this creates one of the biggest challenges in all of computer design. A massive, massive speed gap between the two.
Okay, here's the problem. Modern CPUs are just unbelievably fast. Main memory, our RAM? Well, it's not even close. So if the CPU has to stop and wait for RAM to deliver every single instruction and every little piece of data, it ends up spending most of its time just sitting there, twiddling its thumbs. This is a huge performance bottleneck. So how in the world do we fix it?
This problem is so well known and so significant that it has a name: the memory wall. It's that performance barrier you smack right into when your lightning-fast processor is constantly stalled, just waiting around for the much slower memory to catch up. A super-fast CPU is totally useless if it's being starved for data.
And the solution is genius. It's called cache memory. Cache is a small but extremely fast bit of memory that sits right next to the CPU, and it stores frequently used data. The whole idea is simple. If you've used something recently, chances are you're going to need it again very soon. Think of it like this. RAM is the pantry down the hall, but the cache is the ingredients you've already prepped and put on the countertop right next to you. It makes the whole process so much more efficient.
So far, our instruction's entire journey has been inside the box. But eventually, the results of all this work need to get out into the real world through your keyboard, your mouse, your monitor. This brings us to the world of input and output, or I/O. So how does a super fast CPU talk to something as slow as, say, a keyboard? Well, the simplest way is called programmed I/O, or just polling. This is where the CPU just constantly asks the keyboard,
Got anything yet? How about now? Now? You can imagine how much time this wastes. A much smarter way to do it is interrupt-driven I/O. Here, the CPU just goes about its business, and when you finally press a key, the keyboard sends a signal, an interrupt, that's basically like ringing a doorbell to say, hey, I've got a keystroke for you when you're ready. This frees the CPU up to do useful work instead of just waiting around.
Interrupts are a massive improvement, for sure. But we can push this efficiency thing even further. What if we could reduce the CPU's workload so much that it's barely involved in these data transfers at all?
Right, because even with that doorbell system, the CPU is the one that has to answer the door and carry the data, the groceries, from the device into memory. And that's still a distraction from its main job of, computing. So the question is, can we delegate this chore entirely?
You bet we can, and the solution is called Direct Memory Access, or DMA. With DMA, the CPU basically tells a dedicated DMA controller, hey, you, move this giant chunk of data from the hard drive into memory and just let me know when you're done. The DMA controller then manages that entire transfer all by itself. This is exactly why your game can load a massive new level from the drive while the music keeps playing smoothly and the mouse never freezes. The CPU is free to keep everything running while the DMA controller does all the heavy lifting in the background.
Okay, we've followed our little instruction from the CPU through the whole memory system and out into the world. Now, let's just take a step back and see how all these pieces perform together in one final coordinated act.
So think about it. From that one single click, an instruction is fetched, probably from that super fast cache. It gets decoded and then executed. If it needs a big chunk of data, a DMA transfer kicks off. An interrupt rings the doorbell when it's done. The CPU processes that new data and sends the final result to your monitor. It really isn't about one component. It's a beautiful symphony of all of them, working in perfect harmony.
And this quote from our source material just hits the nail on the head. It's not about any single part in isolation. The real magic of a computer comes from its structure, the way all these millions of tiny parts relate to each other, passing data and control signals back and forth at just unbelievable speeds.
So we've seen this intricate dance that happens inside our machines today. But every single component is getting faster, smaller, and way more specialized. It really leaves us with a fascinating question to ponder. What new levels of performance, what new kinds of magic will the computer symphony of tomorrow be able to create? What's it even going to sound like?